Section. Introduction. We're going to talk about large language models, LLMs, which have shown great potential in a variety of tasks. However, the real challenge lies in adapting these models to tasks that have limited resources. One way to do this is through parameter-efficient tuning, PET, a method that introduces task-specific weights to the base model, allowing it to learn without forgetting previous knowledge. This method is not only more effective but also less costly than in-context learning. One popular PET method is LoRA, which uses low-rank matrices to achieve high performance. But there's a question that users of LoRA or any other PET method often ask: how many trainable parameters should we use? In LoRA, this is determined by the rank of the low-rank matrices. Increasing this value can provide more computational power for specific tasks. However, it's been found that using higher rank matrices doesn't necessarily improve the model's quality due to training instability. This is a hidden bottleneck that remains a challenge to overcome. Another approach is to use sparse mixture of experts, SMOE, in neural networks as a replacement for feed-forward networks. There are various ways to assign experts to tokens, including reinforcement learning, linear programs, fixed rules, and soft assignment. Some recent studies have suggested using mixture of expert models on top of parameter-efficient tuning. However, these studies have overlooked the potential of sparse MO, possibly due to issues like token dropping and overfitting. In this paper, we propose a new method called SiRA, or sparse mixture of low-rank adaptation. SiRA uses sparse computation for PET and enforces the top K experts routing, which improves resource and computation utilization. It also allows for more fine-grained control of a given input. SiRA has three key components: a capacity constraint that allows for token dropping, an auxiliary loss to penalize overuse of a few experts, and a novel expert dropout mechanism. These components work together to balance the load and prevent overfitting. We've conducted extensive experiments to test SiRA's performance, and it outperforms LoRA and its MO variants Adamix, MLoRA across a wide range of single-task and multitask benchmarks. Our study showed that the number of used experts and capacity per expert improves performance, demonstrating the advantage of being sparse. Notably, the expert dropout plays a crucial role and is more effective than SMOE dropout. There are various types of parameter-efficient tuning, such as adapters, prefix tuning, prompt tuning, p-tuning, attention injection, LoRA, and combinations of PET methods. In this paper, we focus on LoRA as it has been found to achieve better results, although our methods could be applied to other types as well. Adamix and MLoRA are two methods that combine PET and MO. Adamix randomly chooses an expert during training and averages all the experts during inference. While this method is efficient, it doesn't allow the experts to specialize. Moreover, the random approach significantly increases the training time. MLoRA, on the other hand, applies the full soft MO on top of LoRA, where all experts are averaged using a learned gating. Compared to these methods, our method, SiRA, is more efficient. It doesn't require more training time than standard LoRA and enforces sparsity, which saves training resources and computation. We propose a new method called sparse mixture of experts of low-rank adaptation, SiRA, to increase the capacity of LoRA using mixture of experts, MO, without adding too much computational cost. SiRA uses multiple lightweight LoRA adapters as experts while enforcing sparsity when using the experts. The MO layer for the adapter consists of E experts, each with their own LoRA weights. We also assume the base foundation model has its own frozen weight. Next, we will introduce each component of our framework that enforces the sparsity of LoRA experts. Section Summary. Large language models, LLMs, have shown impressive capabilities, but adapting them to low-resource tasks is crucial. Parameter-efficient tuning, PET, methods like LoRA have been successful, but determining the optimal number of trainable parameters remains a challenge. In this paper, we propose SiRA, a sparse mixture of low-rank adaptation, which enforces sparsity in the mixture of experts, MO, layer of LoRA, resulting in improved resource utilization and performance compared to existing methods. Section. Expert gating. In our study, we introduce a method called SiRA, which activates only a subset of all expert modules to reduce computational cost. During each forward pass, we select a certain number, K, out of all E experts. This selection is based on the output scores of a gating network, which we denote as theta_G. This process is mathematically represented by an equation, where S represents the token index of the sequence X, and G_S, E, is the output of the gating network at the STH token for the ETH expert. To make the gate more balanced, we propose a simple gate dropout method. This involves introducing dropout to the gating output, G. We also enforce capacity constraints for experts, following the GS-hard method. This means that the number of tokens processed by each expert should not exceed a predefined threshold. If an expert reaches its capacity, it will drop the overflow tokens. If all K experts reach their token capacity before all tokens in a training example are processed, the remaining tokens will be encoded using the frozen model parameter, W_0. We also define an auxiliary loss term to encourage load balancing among different experts. We denote the total number of tokens as S, and there are E experts. The number of tokens routed to expert E is denoted as C_E. We use the mean gates per expert, M_E, as a differentiable approximation, and define the auxiliary loss in an equation. We compare our model with standard models like LoRa, Atomics, and Melora. We don't compare with other adapter approaches as the SiRA approach could be applied on top of them. We use the PALM2FLANXXS as the base model and follow default configurations to inject LoRa weights on the attention projections. We set the intrinsic rank as 4 and use 16 experts by default across all baselines. We evaluate our model on several datasets, including XtremeUp, Finca, and ForumSum. XtremeUp is a multilingual multitask dataset focusing on underrepresented languages. We choose Swahili and Bengali for our evaluation. Finca is a QA dataset in the financial domain, requiring complex reasoning capabilities. ForumSum is a conversation summarization dataset with human-written summaries collected from various internet forums. Our evaluation shows that SiRA outperforms all other baselines in most tasks, with less than 1% extra parameters. Notably, SiRA consistently performs better than Melora across all tasks, demonstrating that a sparse mixture of experts, MO, is better than a full MO. Atomics shows a small advantage on the semantic parsing task, but overall, SiRA performs better across all other tasks. We also conducted experiments on 2 multitask settings on Swahili and Bengali, and 2 multilingual settings for QA tasks. The overall trend is similar to what we found in the single tasks, with SiRA achieving the best average performance among all baselines. We also share ablations on ForumSum. We found that increasing the computation or the capacity does not always increase the scores. There is a comfortable zone, which we need to find out with model tuning. This justifies why the full MO-based approach is not as good as SiRA, which provides more fine-grained control on the computation. Section summary. SiRA reduces computational cost by selectively activating a subset of expert modules using a gating network. It introduces gate dropout to balance the gating output and enforces capacity constraints on experts. SiRA outperforms other baselines in various tasks, demonstrating the effectiveness of its sparse MO approach. Section. Gating ablations. We've conducted several tests to understand the role of gating in our SiRA model, and the results are summarized in a table. We compared our model under 3 different conditions. 1. Without the auxiliary loss. 2. Without the gate dropout, and 3. Using a static routing-based dropout called SMOE dropout. The findings suggest that a learned gating mechanism outperforms a fixed one, and both the gate dropout and auxiliary loss contribute to SiRA's performance. To further understand what the gate is learning, we conducted a Swahili multitask experiment. We calculated the average entropy of each gate weight distribution before applying the top K function. The average entropy for the question answering task, conducted in the Swahili language, decreased from 1.6 to 1.13 nats during training. This suggests that the model is learning to assign more weight to certain gates as it trains. We also calculated the average correlation coefficients between each task index and each gate index. For this, we converted the task index into a one-hot encoding. At the end of training, the average correlation was about 0.025, which is not significant. Similarly, the correlation between gates and languages in the multilingual experiment was also not significant. This implies that our gating mechanism does not learn to route different tasks to different gates. This paper is a work in progress. We're planning to gather more results, conduct further analysis, and improve the writing. We're open to suggestions, insights, and constructive criticism from the research community. If you have any feedback or ideas that could potentially improve the quality and impact of our work, please feel free to reach out to the lead author. We value your input and are keen to incorporate diverse perspectives to enhance and advance our research.